Well, what we have here tonight is a beautiful Heathkit IG1275 Linear logarithmic sweep generator. This was one of the more complicated of the instrumentation packages, especially in the generators area that Heathkit came out with. More aggressive calibration on this was really something. The unit provides signals from 3 Hertz up to about 3 megahertz, and it'll provide that in 6 ranges. So you can dial in whatever frequency you'd like to have it. It's an audio generator on up to the low RF stages. It also provides a number of other functions. This is a square wave generator, a triangle wave, a sine wave generator. It'll provide it continuously. It'll provide it gated, where we'll demonstrate that in a little while, but you can, upon demand, push a button and throw through pulses. You can get bursts of pulses, and you can control the number of cycles in each burst. And then the linear and log sweep. You can sweep at a linear rate, or you can sweep at a logarithmic rate. You can adjust the symmetry of the waveform. Vary the way that it looks, the attack and decay of the waveform itself. You can provide an offset to the wave. You can add DC offset, raise it, lower it, or you can leave it right on the line through its middle. And then we have a calibrated attenuated output. 6 different steps of attenuation, 0 through 50, into a 50 ohm input. You can get 10 volts peak to peak. And then you have a continuously variable attenuator as well. It's kind of a Swiss pocket knife of generators in the audio to low RF range. Be a wonderful thing to use for testing out amplifiers, testing out frequency response of various circuits you build. Filters would be a big one for audio to the low RF range. So it's in very nice shape, beautiful case. Nice bright Heathkit blue color. Good set of controls on the front, sync output, external trigger input, output here. And then, looking at the reverse side, we have a sweep gate output, sweep output, analog output, and a voltage control input. So you can control this with an external voltage to do whatever the heck you'd like it to do. Anything that you can control, as long as you can provide the voltage, I believe it's 0 to 5 volts, you can sweep this generator anywhere you'd like. So provide a complex voltage change and you would get a complex set of signal changes. It'll come with a manual. It's a rather significant manual. Goes through the construction first of all, whereabouts of all of the parts, identification of the parts, and so on, as Heathkit does. Then it goes through the calibration. Like I said, it was a rather lengthy calibration and pretty complicated. Some testing, construction of the box, and then operation, and there's some theory of the circuitry and so on. There's specifications, a large number of 8.5 by 11 fold-out pages, so you'll have component layouts and schematic diagrams and so on. There we go. So everything you would need to own, operate, modify. The rest would be using your own inventiveness to figure out what to do with it. So anyway, we're going to go and test this thing. It's, like I said, it's rather exciting. We'll run you through its operation. Bear with me a moment, and we'll hook it up. Okay, we've hooked the sweep generator up to this B&K oscilloscope up here. And at the moment, we are on the lowest range. We're on 10 to the first power, so whatever's on the dial is times 10. And currently we are reading somewhere between 0.03 and 0.3. But according to my oscilloscope, we're putting at about 1 hertz. So we're getting about 2 divisions per cycle, and we are on the 0.5 seconds per division. So that would be 1 second in 2 divisions, and that would be 1 cycle. So we're at 1 hertz right now, 1 cycle per second. Now we're going to go ahead and boost her up. Let's take her up to, let's see, 20 hertz. We are reading, okay, there we're getting 2 cycles and 10 divisions at 10 milliseconds per division. So 10 divisions, 100 milliseconds divided by 2, 50 milliseconds, that would be 0.5 seconds. So there's 20 hertz. And that would be predicted by the dial, since we are running right at 20. I don't believe we're going to be able to see that, but we are on 2 right here on the dial, and 10 to the first. Let's go ahead. That's mid-range roughly. Let's go ahead and take her up to 30. 3 cycles in 10 divisions at 10 milliseconds per division. So there we are at 30 hertz. Let's go to times 10 to the second power. We are at the top of the scale right now, so we'll be reading 300 hertz. And to read that, I am now at 1 millisecond per division. I see that I have 3 cycles across 10 divisions. That's 300 hertz. And that is exactly what's on the dial. Thank goodness. Let's take her down to 100 hertz. That would be 100 here. Let's see how close we can get to 100. Okay. And we are right on the line. There is 1 cycle in 10 divisions at 1 millisecond per division. That would be 100 hertz. Okay. Let's go ahead and go times 10 cubed. And we are right now on 1 times 10 cubed. That'd be 1,000 hertz. That would be 1 millisecond per division. We should get 1 division. And right now we're getting 1 division per cycle. So we are at 1,000 hertz. Let's go ahead and take her up. 2,000, and we would need at 2,000. We're going to get 2 cycles per division in this case, unless I expand it. So let's double it, and we're going to get 2 cycles and 2 divisions now. Here is 1, 2, and it's in 2 divisions. 2 cycles and 2 divisions. This would be 2000 hertz. And I've got connected up here to a frequency meter, and we can see that we are running 2000 hertz. Let's go ahead and take her up to 3000. Okay. 3000, let's go to 0.1 millisecond per division. We should be able to get 3 complete traces. We have, and confirmation digitally, 3000 hertz. Send to the 4th power. We're at 3000 right now. We'll just start right there. And we might as well go up to 10 microseconds per division. 10 divisions, we get 3 cycles. Again, this is great. We are running 30 kilohertz. 30 kilohertz, that would make sense. Okay, take ourselves down to 10 kilohertz. Well, I'm going to put it right on the 1 on the dial. And we see that we are running roughly one cycle and 10 divisions at 10 microseconds. And this would be 10 kilohertz. Frequency-wise, we are off slightly, so with a little nudge of the dial, we can put ourselves at exactly 10,000. All right, and the difference is about, I don't know, maybe 1/8 of an inch, approximately, on the dial. Okay. Let's go to times 10 to the 5th. I'm not going to change the dial right now. We should be running 1 times 100,000, so about 100,000 hertz. And first off, what I see is I'm running 96,390 or so hertz. Let's go ahead and raise her up slightly. All right, there's 100,000. And we are maybe 3/16 off of the 100,000 on the dial. And if I change my scale to 1 microsecond per division, we are crossing 10 divisions. That's 100,000 hertz. Let's go ahead and take her up to 300,000. Okay. We have 3 cycles in 10 division at 1 microsecond. That's 300,000. We are running right now 295,000 on the counter. And then we go to 10 to the 6th, 3 megahertz. This is the top end. All right. We are at 3 megahertz on the dial. We're going to raise our band. We see that we have 3 cycles in 10 divisions. Again. And we are running at 0.1 microseconds per division. 1 microsecond across the screen divided by 3, so 0.3 microseconds per cycle. That's 3 megahertz. And we are getting 3 megahertz on the frequency counter. So that takes us through the manual audio control of this thing. Let's go ahead and demonstrate what we mean by gate. The function is set to gate. I'm set on the sine wave, and I'm not sweeping, but I'm going to, I'm in the 3 million hertz range. I don't see anything on the screen at the moment, but then I'm going to push the trigger button. There. Push the trigger on, let it go, so I can gate it. That's what's meant by that. Now I can go into burst mode. This is the kind of signal you get into burst mode. Let me get the reflection off of there, sorry. And I can change the frequency of the burst package. Actually, the time span that the burst window is on. In between sections, I have signals that I am popping through. We can take a look at here. Okay, we're looking at the burst mode again. And watch, as I control the auto trigger, I can control the number of pulses within each packet. I can take it right down to 1, which I just did. Just make sure we have some intensity here, you can see it. And I can throw it back in again. We can change the style of the pulse. Let's say we go to square wave, sine wave. Okay, here we're feeding in roughly 200,000 hertz bursts, and we're doing it roughly, I don't know, somewhere around 10 microseconds apart. There's 2 pulses. I can adjust my trigger. We can go to 3, 4. Okay, if I go more, now we're going to overlap, so bring her back. So you can see I have some pretty good control over what I have happening with the pulses. We can go to a triangle wave, we can go to a square wave. If I'm going to demo the square wave, we've got to go into DC mode. And probably turn that up a little bit. By simply pulling this knob here, I have an offset control that allows me to control a DC component to the waveform. I can add DC, or I can subtract it. Or I can go right back to having no DC component at all. Attenuation, I can attenuate it right here from my control. It's calibrated. I have a symmetry control. Symmetry controls right here. If I pop my symmetry in, I multiply my frequency, I divide my frequency by a factor of about 10, but I can now control the symmetry of my waveform. I can skew it. So I could skew it, I could move it up and down. I can do any number of things with this. It's more like a trapezoidal wave there. Okay. Go back out. There we are again. We haven't demonstrated the sweep. Okay, so next let's take a look at the sweep. If I put myself into a linear sweep mode, I can decide to leave my sweep limit wherever I wish, and then I move my start limit where I would like it. And sweep time. Let's go nice and slow to begin with. Okay. We see ourselves rising in frequency here. Now let's sweep a little bit faster. Now, one of the things I want you to notice as I'm sweeping is the envelope of the amplitude doesn't change. And if it does change, it's very, very imperceptibly. This as we're sweeping over lots of frequency here. Jump up, I've gone to 10 to the 6th. An interesting sweep. You can see that I start in the low end and then like a spring, I suddenly spring up into the upper ranges and I get more frequency components. Now I should disconnect my my frequency meter. That's going to hamper the high frequency end of it here. Let's So it's an exciting piece. Okay, so here what I've done is my little trick with the 455 kilohertz resonator. I've got the ceramic resonator connected in series to the output, and then going into my probe, I have my scope on XY mode. I'm feeding into the B channel the time base sweep, which comes from the rear of the instrument. I have the sweep output. So I'm tracing my X line, and as I'm tracing my X line, it's sweeping the frequency across the range of what I have selected here, which right at the moment would be sweeping it from approximately we'll say 100 hertz up to about 455 460 kilohertz. And as we see, the input comes in as we're sweeping in our frequency. It's fine until we get to about 455, and then we see these dramatic spikes, top and bottom. That's where the resonator naturally resonates. And then she comes back down, and as we go forward, it flattens out again. So that's just an extreme example of utilizing the capabilities of the sweep generator with your scope and using it to map out the transfer characteristics of this ceramic resonator. Could have been any filter circuit that I was designing. I could have been looking at high pass filter, low pass filter, so on. Exciting use for the thing. Okay, well here we've hooked up a just a little 3-component example of a high pass filter. I'm sorry, right now we're a low pass filter, and we we have the generator outputting a steady signal into the XY scope, and we can see that we're off the screen on both ends. I'm at the extreme low end of my dial. Now as I raise my frequency, we can see the amplitude start to come down, right? So we got the idea that we're passing low frequencies well, but we're not passing the high frequencies so well. So let's go ahead and put this thing into linear sweep and take a look at the transfer function. That's our low pass filter. Now we'll move a couple of components around, the inputs and the outputs, and now we have something of the opposite nature. So as our frequency goes up, we become more effective at carrying the frequency. So we have a high pass filter. Like I say, there's an example of just some of the things you can do with this thing. You can have all kinds of fun studying your filter network theory, testing them out. You could use a, say a capacitor box and an inductor, and you could sit there and tune circuits to any number of different frequencies just by spinning the dial. And you could do a rough calculation, come up with the answer, test it out, look at the response, make yourself happy. Well, anyway, makes me happy. So thanks for listening. Good luck on your bidding. We'll see you again.